Hello, everyone. My name is Shuji Nakanishi from Osaka University. Today, I'd like to talk about dynamic patterns that appear on electrochemical interfaces. Actually, I have worked on these topics about 10 years ago. So I bring here today's a kind of old, story. But I got a request from Nakamura Ryuhei-san to bring this old topics. And honestly speaking, I wanted to decline his request, but I could not do it because he's a good friend. I had no idea how many people have interested in electrochemistry here, how many people are familiar with nonlinear chemistry, and I have no idea about the origin of life. But anyway, I think the organizer expects that we can find something new at the interface between electrocatalyst and nonlinear chemistry. So I try my best to give you some inspiration, and I also want to enjoy myself. So let me start my talk. So first, let me talk about the catalyst. For electrochemistry, the catalysts are generally loaded on electrode surface to accelerate a target reaction. But however, when the reaction are accelerated by catalyst, many factors can be influenced. For example, local concentration, local pH, double layer potential, and even surface area can be changed because of the accelerated reaction. And in general cases, even if these parameters are affected each other, the system will go to the stationary state with long time, right? But when the nonlinearity of the system is significant, the system can reach to new dynamic state, such as chemical oscillation or pattern formation. This is the target of the research I have done so far. So first, I'd like to show some examples of dynamic patterns appearing at electrochemical interfaces. Then next, I guess some of you are not familiar with this field. I'd like to give some fundamental information for understanding the emergence of the order. Because the section 2 is kind of abstract, I'd like to give concrete examples. That is the hydrogen peroxide reaction on platinum. It's a very simple reaction system. And finally, I'd like to talk, or I'd like to dream how this field can contribute to the new science in catalysts. So this morning, we had a lecture by Akiyama-san. So now we are familiar with cyanobacterial clock. And as he explained, the cyanobacterial cell has clock, oscillation inside. So if we can connect the intracellular region and electrode for example, by using a mediator, we can detect the rhythm by electrochemical method. So there are many reported works on this kind of electrochemical oscillation. However, in this case, electrochemistry just serves as a sensor, right? It did nothing for this oscillation. So this kind of oscillation does not the focus of my today's talk. Today, I'd like to talk about a system in which electrochemistry plays an essential role for the appearance of oscillation. This is the examples of a reaction of hydrogen peroxide to reduction to water on platinum. So here you can see that current density exhibit rhythms. But this oscillation can appear only when electrochemistry is used. When some reductant are used for hydrogen peroxide reduction, no oscillation appears. That means electrochemistry plays an essential role for it. This kind of temporal rhythm can lead to the dynamic two-dimensional patterns. For these examples, we use a ring-shaped electrode. This is good for treating these experimental results mathematically because we can provide a periodic boundary condition in both in experiment, in equation, mathematical equation. And depending on various experimental condition, for example, electrode potential and the geometry of the electrode arrangement, many various kind of two-dimensional waves could be observed like this. Although for hydrogen peroxide reduction systems, oscillation appears, but after reaction ceases, nothing have remained there because the product is water. But in case the oscillation are coupled with crystallization, the history of the system are recorded on the electrode surface as a deposit. And because of the periodic oscillating nature of the current, such a beautiful three-dimensional periodic structure are formed in a self-organization manner. Because this is a crystal, even after stopping the reaction, it's stable. We can get it. This is interesting. Another example. In this experiment, the electrode deposition occurs just at the interface of oil and water. And in this experiment, working electrode are put here, and just the tip edge of the working electrode just touch at the interface. So electrode depositions occur just right at the interface. And you can see that the interface are oscillating here, coupled with electrode deposition. This means the interfacial energy also oscillating, coupled with electrochemical reaction. So after finding this phenomenon, we put another experiment to get a water-oil interface by putting oil droplet on the electrode. In this case, because of the dynamic changes of the interface, the droplet, start to move just like worm. And when the application potential are stopped, it's frozen at the position. So like this, in electrochemical systems, we have various kinds of dynamic patterns, oscillation, waves, whatever. But how many chemical oscillator do you know? DZ reaction is the most famous representative system for chemical oscillation. But how many do you know similar to this reaction? For me, I can count with my fingers, just several systems can show oscillation. However, in electrochemical systems, as I have shown so far, a lot of kinds of dynamic structure observed. For example, even for very simple reaction system, hydrogen peroxide reaction on PT, so far 11 different kinds of oscillation are found. So why electrochemical system is enrich this kind of dynamic phenomena? So that is the next target to explain. So before going deeper, I need to give you some very fundamental textbook information regarding the formation of dynamic patterns. I guess some of you know this, but I'm also sure that some of the audience have never seen it. So here, let's consider the system which can be described by this simple differential equation. X dot time differentiation of x is described like this. When the parameter mu is negative, there is one stationary state where the x dot equals 0, so no time dependent state, right? And when x is negative here, the x dot is positive. So the state go to right. On the other hand, when x is positive, now x dot is negative. So the state go to negative side. This means this state is very stable against the fluctuation, right? But in the contrast, when parameter mu is positive, we can get 3 stationary states, and 2 of them are stable just like this. However, this state is very unstable, and like this, symmetry of the system is broken with increasing the parameter mu. So in general, the nonlinearity of the system are increasing when the state is far from equilibrium, right? If we look at this from an electrochemistry point of view, we have more chance to have multiple steady state when overpotential is very high. In other words, we have chance to get dynamic orders in far equilibrium with strong nonlinearity. This discussion can be extended to two-dimensional, two-variable system with x and y as the essential variable. Again, when mu is small, the cross point of two curves are stable against fluctuation. However, when the nonlinearity becomes large, the bifurcation theory tells us a stable cyclic orbit can be stable. Although I will not go deeper to this, it's very fundamental information you can easily find in textbook. But what I want to say here is, with increasing the nonlinearity, with increasing the overpotential, we have chance to have very stable limit cycles around the stationary state. So this figure tells us that the sign of the slope of one variable is critical. Here, the slope is like this, right? But with increasing the mu value, the sign of the slope changes, right? In electrochemical systems, the current density generally increasing with increasing the overpotential, right? However, in some cases, the slope can be negative. And in this case, as I have explained, we have chance to get oscillation here. So the question is when such a negative slope can be obtained in electrochemical reaction. The Faraday current in electrochemical system can be expressed by the product of electron number n, Faraday constant F, reaction rate constant K, surface area A, and the surface concentration of active species C. So now we are interested in the negative value of the slope, and N and F are constant. It never depends on potential. So there are three possibilities to have negative slope. One is dk over dE is negative. This corresponds to the situation shown here. If we have a promoter, catalyst for accelerating reaction, and with increasing potential, if the catalyst removed from the surface, reaction rate will be slowed down. This is the case for the one. For second case, dA over dE negative, it's easy to imagine. If we have a inhibiting adsorbent species on surface and which blocks the reaction, the current will be slowed down with increasing the potential. The last case, dC over dE negative, it occurs when cation is oxidized or anion is reduced because of the electric repulsion between the species and the electrode. So these three cases frequently appear in electrochemical system. That's why, not like the chemical oscillating system, electrochemistry is enriched for such a dynamic phenomenon. So the above explanation is a kind of general abstract. So give me a concrete examples. That is again the reduction of hydrogen peroxide. Hydrogen peroxide reduction on platinum is very active. However, platinum is also active for adsorbing atomic hydrogen. And when platinum surface is covered by platinum, the surface is pacificated and the reduction current is stopped. This corresponding to the case 2, dA over dE is negative. Because of these characters, negative slope appears here, and when the parameters are tuned, oscillation appears. This can be modeled very simple equivalent circuit. Now we are doing electrochemistry, so the potential U are fixed at the constant, and U can be divided into double layer potential and ohmic drop. And the current flowing a system are sum of the charging current and the Faraday current. Okay. So in this equation, the time differentiation of double layer potential appears in the charging current. So now we got one differential equation. Another differential equation is about the concentration. It's first term is for diffusion, second term is for reaction. And in this system, reaction is suppressed by adsorbed hydrogen. So here the inhibiting effects are taken into consideration. And this, of course, this is also included in Faraday current. This is very simple equation. Although this is very simple, it reproduces the experimental results very well. And we can also get the, two curves I have shown before. And you see the cross point here, it's on negative slope. And we can also get the limit cycles here that tell us double layer potential and the concentration oscillate each other. And the important point is, if we have not considered the suppression effect by hydrogen, limit cycle never appears. So, like this, in electrochemical system, the oscillations easily appear like this. This model can be extended to two-dimensional spaces, just connecting the equivalent circuit like this. And not only the oscillation, but the two-dimensional patterns are also reproduced very well. like this. Some of you might find for these two cases, spatial symmetry is not broken, but these four cases, the spatial symmetry is broken. It's already clarified what is the determining factor for this symmetry breaking by German groups. That mechanism is very specific to electrochemistry, so I don't like to go deeper, just to show you the essence. Because of the function of the potential stat, which try to keep the potential between working and the difference electrode. Because of this function, when one position of the electrode is activated, other positions are globally suppressed. By this mechanism, spatial symmetry can be broken. But although this is very specific to electrochemistry, I will say this can be generalized to other systems later, and which might be attract the people who have interest in origin of life. Let me show another interesting system that is called excitable medium. I have already said many times, limit cycles, oscillation appears on the negative slope here. But now let's consider another cases. Here the cross point is on positive slope. So no chance to have rhythm, no chance to have oscillation. But in case this position is very close to negative slope, this system have a chance to activate it only once by external stimuli. So here, let me show a movie. Before starting movie, I need to explain the blue color means the reaction plane is very passive, nothing happens. Then later, the center position is activated, stimulated. Okay, then let's see what happened. Now everything is quiet. It's so quick. After 1 second, on this calculation, local stimulation are applied. And now you see nothing happened, right? But still, movie is working. That means it's very quiet, nothing happened after one activation. Let me play again. See, it can be activated only once. But interesting phenomena can appear when global suppressions are applied to this excitable medium. In such a case, the case with global inhibition, isolated reactive spot appears and it never disappears. And depending on the degree of the global suppression, in some cases, this active spot can be fixed at a certain position of the reaction plane. So this might be interesting because if such an active spot are stabilized at one position, that means at the interface, we have a gradient of electric field, concentric field, something like that. That might be trigger the second process, even in homogeneous, spaces. The important point is we have two variables to get excitable media, and in addition to these two variables, if the third variable which can quickly and globally affects on the larger spaces, we have a chance to get stable gradient at homogeneous plane. So now let me dream about the future. I want to try my best how to combine with this field and the catalyst chemistry. The attracting point in this system is the orbit is very stable against fluctuation. So if we can design or we can achieve such kind of dynamic system, catalytic system, it can be expected the system can be very robust even under fluctuating condition. So for examples, design reactor with and without oscillatory networks. In case the reactor has chemical oscillator inside, of course the output will oscillate. Right? However, because of the limit cycle nature, we might be able to expect such a system can be stable even under fluctuated conditions. But on the other hand, for the case without oscillation networks, the system might be very fragile. I mean, the output can be scattered when the system is put in the natural environment. The cyanobacteria, which Akiyama-san talked today, might be such a reactor because thanks to the many cyanomicrobiologists, clock deficient mutants are available. And here I bring one slide with experimental data, but because of the recording the video, I give up to show the data in front of you. So, but if you have interested in, just call me. I can show the data. So it's almost time. One message that in electrochemical system, we have many chances to get oscillation. This is because negative slope on double layer potential can be easily obtained in electrochemical system. But another possibility is that negative slope on concentration, not on double layer potential. This situation can be satisfied when the reaction has autocatalytic nature, or in other words, twin generating reaction. In this case, this is rare, as I said. We know only a couple of systems, right? But it's not impossible. Recently, Whiteside group have successfully synthesizing the oscillator, I mean twin generating reaction. It's very great, I mean wonderful works. And I think this is the first example of chemical synthetic oscillator. And if we look at this reaction, actually there are twin generating reactions are involved. But for Folomorph reaction, that's also famous. Again, here you can see twin generating reaction. You can find a mother here. And this bond is broken and a twin are generated. And such a twin generation reaction are very typical for cyclic pathway in cellular metabolism. If you look at the textbook, all the cyclic pathway have twin generating include twin generating reaction. Like this, the key for the success of the achieving a limit cycle in chemical reaction is to get twin generating reaction. And I think this might be one of the possible direction for developing a catalyst with homeostatic robustness under fluctuating environmental condition. For achieving this, we need to understand the mathematical structure behind the experiment. This is very essentially important. And so I believe that deeper communication between mathematician and the chemist might be helpful for developing such a new field of science. Actually, I could do nothing without him. He's a mathematician, the professional in bifurcation theory. And also, I got a lot of inspiration from Professor Carl Johnson, he's a biologist, but think a lot about the appearance of rhythm. And I also say thanks to my supervisor and the colleagues here. And I'm happy to dream with all of you about the new direction of Catalysis. That's all. Thank you very much for your kind attention.
So, any questions from the audience? So actually, I'm impressed by your sketch. It's like I'm receiving a lecture. So I saw there's a lot of equations and figures that drawn by yourself.
Yes.
Yeah, it's very interesting. Mm-hmm. And actually, so in regard to the autocatalytic system, we have a problem about the dilution of some of the reactants.
Yes.
You just said the system can be robust if there is oscillation. Can we overcome that problem too?
I don't think so. We have to supply the substrate, continuous substrate. This kind of behavior can appear only in non-equilibrium condition.
Okay.
So we need to energy input or substrate input.
I see.
Yes.
Okay.
This is necessary.
Okay. Okay.
Thank you for the wonderful talk. I think it's clear from the presentation, but I just want to make sure explicitly. So in order to make, for example, a robust system, we need, in your equation, you showed that the Faraday current must decrease with potential, right?
Say again?
You showed the Faraday current, IF, must decrease with potential, right? And that's necessary for the robust system. And so I want to kind of confirm explicitly that that means we need to sacrifice catalytic activity for robustness, right? We need to sacrifice, right? This is what you mean.
I don't catch your point. You said there is a trade-off relationship?
Yeah. So
why you think
DIF over DE must be negative, right?
Yes.
For robustness. That means
yes.
Catalytic activity must decrease. Usually you want DIF over DE to be positive. You want that as high as possible.
Yes.
And that's very efficient catalysis with respect to driving force.
Yes.
But here you say for robustness, you want the opposite, right?
Yeah, but I'm talking about the slope, not the absolute value.
Yeah, of course not absolute value.
Yes. So but it does not mean there is a trade-off. We can satisfy both high reaction rate, just the slope is negative.
But that,
it's okay.
Okay, but anyway, you need a negative slope, right?
Yes.
Okay. Yeah.
Yes.
I understand.
That's essential.
Okay. Yeah. Does the hydrogen peroxide oscillation work in reverse?
What?
Does it work in reverse? If you oxidize water to hydrogen peroxide, the reverse reaction.
I don't think so, because
why not then?
Why not? It's because for hydrogen peroxide reduction, the potential range is within the potential where hydrogen adsorbs on platinum.
Okay.
So we need two necessary conditions.
Yeah. Okay.
One is the hydrogen reduction, and one is the hydrogen adsorption on platinum.
Okay.
So these potentials are overlapped. That's why we got oscillation.
On that particular catalyst. Yeah. Okay. I see. Ask another. Can you make one of your oscillating reactions influence another one in a cascade? Right now, the products are water, not that useful, but could you make one actuate another one?
I don't know. You expect
Amplification? I mean, you know, again, you could think about all the things we do with electronic circuits, with
Yes.
oscillating outputs.
Yes.
We amplify them, rectify them. We do all sorts of things with them. Could you
Yeah.
build a computer with the outputs of your, and do computations with your the outputs of those types of reactions? You have a clock, just like our microprocessors.
Yes, I'm not sure I can catch your question
Okay.
correctly, but during oscillation,
Yeah,
double layer potential
yeah,
and the concentration of one specific
yeah.
species interact
Yeah.
each other.
Yeah.
This is the most simplest cases.
Sure.
But in a more complex system in which multiple reactions play part in,
Yeah.
everything will be connected. It can form some networks and cascade reaction can be
That
triggered.
might be quite interesting. Okay, so
So we almost time. Almost time. So let's thank Professor Shuji Nakanishi again.
Thank you very much.